Hello everyone, how are you guys doing? Today we're gonna continue with our Learning to Research episode 4, designing a hover vehicle. Today we're gonna calculate the power required to, operate this drone. And right now, what I need to do, if you haven't caught up with the earlier episode, just go watch it. And if it's too long for you, I've given you a gift right here. I've written down everything on a blog right over here, and boom, use this. So when we left off yesterday, we already calculated the minimum maximum payload. For that, we used the world population. We calculated the average weight of each human in each continent. From there, we calculated minimum mass and maximum mass threshold. From there, we calculated the minimum and maximum thrust using North America and Asia's weight. And from there, we know the design parameters for thrust. That's where we're at. So now we need to use like a quadcopter design to actually calculate the theoretical thing. And if you don't have time right now to watch the whole video, what I'm gonna suggest is you're gonna click this. The blog link is given below, and you can just watch this, read it, and power through it easy. And if you have time to listen to me rant and rumble and explain to you how I did it, and if you ever feel like my explanations in the blog are not adequate, you can always come back to the video and you can learn. Let's begin, okay? So for this, we needed a little bit of literature review. For that, I used this thing over here. I used this resource over here, and internet is such an easy thing. Before, I used to have to go to libraries. Now at one click I can find like a PDF. So I use this one, okay? And it's gonna take like hella long to download this. I'm just gonna leave it for now. And for your ease, I know that was gonna happen, and I use this website. This is very easy. How much power is needed to hover? I use theirs. Visualizing thing, and this was very easy. So let's look at this picture for a minute, okay? I've given them credit, guys. So if you have a quadcopter like this one, it rotates, right? When it rotates, it creates this cylinder, right? It creates a cylinder. That means it has a certain area it's going to push into it. It's not going to push this way. It's not going to push it. It's going to push downwards. That's the principle, right? For different rotors, or let's just talk about one motor, is pushing down. It creates the cylinder. It's going to go downwards. We're assuming it's an ideal case. Let's begin. So you know the volume of a cylinder, right? Pi r square h. Pi is pi, I is radius, and h is height. So you know this. This is a cylinder. That's what is exactly creating right now. Radius is given by the rotor of the blade, or the arm, or the blades, whatever. And height. How do you know the height? Or can you measure it because height keeps changing? No. What you do is very easy. You use the velocity of the air going downwards, and you multiply that by time. Basic instinct. You can do that. It's very easy. The units cancel out, and how we are estimating it is because when you have a cylinder, right, and then it goes to a certain height, and it's gonna move upwards, correct? That's how you're gonna do. So V equals U plus AT, right? Use these equation. You use the fundamental equations of motion, and you can calculate everything else. So U is going to be 0. You can calculate the V using your gravitational thing, and then you're going to calculate the time. Let's say 300 seconds or 9 seconds, 10 seconds. You can calculate it. You can calculate the velocity, but you are not calculating the velocity of a thing going downwards. You're calculating the velocity of air, right? So for that, how do you calculate the velocity of air? For all these, we have the following equations over here. So first off, let's start off with the first equation that we're going to use. And based on things we already know, okay? It's very, very easy to start off with things you know. So what is efficiency? Why can't we have 100% efficiency, okay? First of all, I'm going to explain you what efficiency is. When you have a machine and you put, and you push, let's say you're going to push this laptop that I'm using currently, you want to push this with 10 Newton force. And for some reason it only resists you, or it only moves for a certain amount of area or a certain amount of space, and my result of my actions is only resulting 9 Newton. Where did that 1 Newton go? Entropy. You cannot always at any given time have 100% efficiency, right? So using a non-motor case, we want to calculate the ideal thrust, right? We already have the amount of thrust generated, that the one we need, and we need to calculate the ideal thrust. So that means if you use a motor of 1000 watts and 1000 watts generates 4500 or 4750 Newton, that's not going to cut it, because there's going to be pressure losses, there's going to be tons of issues. That's why you need to aim high. You need to use like a motor of higher capacity. That's why you need efficiency. From that, what we know is 4750. Rearranging this equation, where we get at is we're gonna get thrust generated over efficiency is going to equal ideal thrust. This is the one we use to calculate everything else, right? So where did I get the efficiency 50%? Okay, I'm such a son of a bitch that I use previous research to do that. Okay, according to the Department of Energy, right? Any motor is good at 75% efficiency of rated load, but motors are designed to run at 50 to 100%. And me being me, I go for a higher factor of safety. I chose 50% efficiency. Trust me guys, when you're actually designing it and operating it, you can control the amount of thrust, but you can't generate thrust of like 4750 Newton if your thing only generates about like what 3400 Newton. You can't go above your maximum. So you want to create the highest maximum, you can always go lower, and you can create sensors to curtail it, so that using this formula at 50%, and how to calculate that, I don't want to treat you fractions. We got it at 9500 Newton. We just recalculated everything and rearranged it. So now we can calculate the power of the motor. So how do we calculate the power of the motor? Power of motor is equal to ideal thrust times velocity of air. Now where did I come up with this kind of equation, right? So what I'm gonna do is do a little bit of a, so I use this research over here. I'm gonna talk about it a little bit. Mechanical power formula. Just trust me, I know these things because I went to school for it. So yeah, if you use the cos theta and everything else, since it's going downwards and upwards, I think it's cos 0 or something, or cos 90, I don't know. But anyways, in our case, I did that calculation yesterday. In our case, power is work over time, right? Energy generated over time. Work is force times displacement over time. Force, if you remove it, which is thrust for us at our current situation, displacement over time, force times velocity. Boom, done, easy. So power generated is that, okay? We can now calculate the power, right? But we don't know the velocity of air. We know the ideal thrust. We calculated that just now. We don't know velocity of air. That's why we need to calculate the volume energy generated, right? So what is energy generated? We're going to go into that. So to calculate the velocity of air, we need to calculate the energy generated. So for that, so the energy generated by air that pushes it upwards is what creates the thrust, right? So you have the mass of air, right? And the velocity of air, and you use the energy generated formula. That's the energy generated. Now, we still don't know what the velocity of air is, but we do know how to calculate the mass of air. How do we calculate the mass of air? Which is the volume of air times the density of air. How do we know that? Formula of density. Mass upon volume, you volume times density. Not that hard. I don't even need to quote this, but I did. Right over there. So we're here, right? You understand that? Now, volume of air. Remember what we were talking about, the cylinder? Volume of air is the volume of cylinder created by this rotor. So we already had done that, which is pi times radius times velocity times time. I calculated that earlier. So we go here, we know the mass of air is volume times air, and then volume of air is pi times radius times velocity times time, right? Now, energy generated, you see this equation? Energy generated is mass times air, right? So we substituted this value right here for mass times air. Okay, you understand that? Everything else is same. Everything else is same. Mass times air. Mass times air. This is substituted here. That's all I did. Then what we're going to do is we're going to move a step forward. And instead of using just volume of air, what we're going to do is we're going to use the velocity of air, radius, time, and everything over here. And then we're going to substitute it. Instead of this, we're going to use this value. Pi times radius times velocity of times time. Now this is velocity of air. I'm going to, because it might confuse you over here, I'm going to write velocity of air. We're still stuck in the same idea that we do know radius. We can choose the radius, right? We can choose the time. We can like figure out density of air. I'm going to get into that a little bit. But then we can't choose a velocity. We have to calculate it at first, given the thrust and energy generated. We're still stuck at the same idea. We still don't know the velocity of air. But like, what's the equation that relates us to velocity of air and thrust? An ideal value of power generated. And energy equals power generated over time. Okay? So, power generated equals energy generated over time. And then from where power generated also equals ideal thrust and velocity of air. Right? We calculated this and I explained this to you earlier. So from there, we're substituting energy generated over time with this equation over here. Okay? Right over here. Now there's time, and time cancels each other, and you get this equation. Simple. Which is equal to ideal velocity of air and velocity of air. This velocity of air and this velocity of air cancels each other, so you're left with this equation right here. Simple? Simple? You understand? Not that hard. If you had problems, just go rewind or go look at the blog, do whatever. Now, what are the unknowns and the knowns here? Right? We know from the calculation of ideal thrust, the time of flight we can estimate, right? Which we don't know, it's already eliminated. For the radius, I've explained here. We're going to have to choose a radius for ourselves because we're choosing a design. For me, I became a son of a bitch and did this. I hacked it. I'm a hack. That's who I am. If you really look at this part, okay? Look at this figure. This dude is using this vehicle right over here. And it looks a lot like a bike tire, doesn't it? I thought so too. So why go and design your own rim width And rim diameter, I just chose a rim diameter over a bike. And these are very easy to find. And I think instead of mounting a different thing, I can just ask like a, if I really wanted to go manufactured, I can just ask some manufacturer to do that. And I chose a rim diameter. It's just basic, and these are mechanically made, and these are machined. So there must be, and they're really cheap to make. That's what I thought. Choose some standard design in that, and I chose 18 inches. That's what I chose. Uh, Diameter. So radius is x, diameter is x. So if your diameter is 18 inches to meters, so if your diameter is 18, so you do 18 by 2, you get 2286 meters. That's what I used here for the radius. Okay? Cool? Capiche? Good. Now, to calculate the velocity of air, I'm going to rearrange this equation that we built. So you're going to get the velocity of air, and I'm going to rearrange the equation. This is how it looks like. And then getting the root over. Now I can finally calculate the velocity of air. Ta-da! Now you must be thinking, where did I get the density of air? Funny thing. The internet is such a good resource, and I'm going to talk to you about density of air, right? So air density changes with temperature and pressure and altitude usually changes pressure, so it's redundant. So at 20 degrees Celsius, your air density is going to be 1.204. Okay, you can use this and you can go ideal case, but for sake, like calculation sakes, I'm doing that. So doing this calculation right here, I'm gonna do it for you. Two times square, okay, 2 times thrust divided by pi times r squares times rho, which is the density, bracket divides this, and turn multiply is square root. Square is 0.5, 309.97, 398. I'm rounding off to write it down, but I use this to calculate that. From there, I calculated 9500 times this. Since the units cancel off and the unit of power is watt, I'm going to use that. Where did we get this formula? Power generated is ideal thrust times velocity of air. That we're calculating this much wattage, right? It's crazy. So since this is just one motor, if we just use this one rotor and one thing, we did that wouldn't be good. So we're going to divide it into 4 because it might generate heat, it might lose a lot of efficiency and everything else. We're going to divide that by that. So you're going to get, if you divide this total watt divided by 4, you're going to get this much watt. You convert watt to HP. I don't do calculations on my own. 987.25 approximately. See? So if you really look at it, 987.25 watt, that's crazy, right? Extremely crazy. Let me show you what that is. That's a giant ass motor. But I've got a solution. Remember I was talking about steam powered turbines? I'm going to explain to you something else, okay? I'm going to leave this here for a second. Density of water vapor. So you have 100 degrees Celsius, it becomes 958, right? Huh. Let's just go here. Much easy. I hate units. Do you want to convert? No. So if I do use density of air, so density of water vapor is indeed 958 if you really look at it. So if you replace, you find a higher density, you know, if you find a higher density vapor or gas, you can actually create that. So what I was thinking earlier, initially, was we're gonna be stuck with not using a gas, so we need to figure out something else, right? Can we use carbon dioxide? No. So what I'm thinking right now is using steam to actually power the motor so that you don't have to carry a lot of baggage like that. So what I was thinking was using rocket propulsion. Using rocket propulsion to actually um basically like a jetpack mechanism to generate power so that it can like actually go upwards. Obviously we don't need that much amount of thrust as much as you're seeing right now, right? Superheated steam, so we could use superheated steam, I don't know, but then you'd have to store it and you have to do all of that. This is the type of engine we might need to use. I don't think the whole technology has gotten that far. So that's where we're at we're gonna you have to use like 1,000 HP motor to do that. And if I did something wrong, guys, just let me know. I'm not an expert at this field. I'm just doing whatever I know, and I'm just researching and using my math to calculate all of this. And if you feel like there's something wrong that I did, or if I can improve, just let me know. Now, for the rocket power or steam powered or superheated steam based like hover vehicle, we're gonna explain that in future when I finish the calculation. The part 3 is gonna come a little bit later. For now, we're stuck at this, and we're gonna continue powering through and then figure out how to do all of this. And for your information, just go to Defer the design over there, and look at it. If I have anything wrong given in the blog, just do that. I know this part is wrong. I left this equation. Oh no, not this part. Yeah, I left this time right here. The calculations are correct, but the time part is left out over there. So I'm gonna improve that. But other than that, I'm pretty sure you guys can figure it out. Okay. Good, good. Hope to see you next time. And if you want to add some more, do some more. I'm gonna pause with this particular design until I figure out how to do the rocket calculation and like the engine design and calculation for that. And it's gonna take a little bit of time because I don't want to do like an ideal case only. I want to do the mass flow rate and everything else, and it takes a little bit of time to do that. You have to calculate like phase diagrams and enthalpy. What I was thinking was, let me just go through my train of thought. So you have your phase diagram of water. So I'm going to show you what I was thinking earlier with the steam turbine thing, right? So instead of a quadcopter, so instead of a quadcopter pulling air from above and then going below like that, what I was going to like do was enclose this in a turbine or a nozzle, something like something like that. So the gas enters and it goes through this nozzle and then just woof, goes down and pressures down, and then that's what creates the motion, and that's what creates the thrust. Okay, there are different types of nozzle. That's why you need to do it. So your inlet and your turbine outlet. That's what's gonna drive it, and that's what's gonna drive the motor, and that's what's gonna create the thrust. That's what I was thinking. Okay. But then again, this is how it looks, and that's what I was thinking of doing. So using the phase diagram, right? If you could store vapor, and let's say vapor, the boiling point, let's say we go to 120 degrees. Let me expand this so y'all can see this. Okay, you can see this much more clearly. So in that earlier phase diagram, right, we are at 100 degrees. Now imagine this. This is the boiling point of water, which is 100 degrees. You go here. Vapor, right? Vapor, your temperature. But then you go past it. Right? You have high amount of pressure in a cylinder, and then it's liquid. That means it's got a like you can't store gas like crazy, right? But then you can store like, let's say 30 kg or 30 liters of water like that. But then as you decrease pressure but then maintain the temperature, it's going to create a steam. And what that steam does is it goes through this inlet. That's the gas entry. The steam goes through, you create a pipe, and it creates that motion, creates that thrust. It goes out of this turbine and creates an exhaust gasket, and it creates that it moves the rotor, or it moves the blades. It's going to create the thrust. It's going to create that motion. It's going to make the vehicle move upwards. That's what I was thinking. That's the idea that I was proposing. Comment down your ideas below, and then we can think about that, and then maybe we can collaborate and do that. I'm thinking like that. I don't know. I'm not an expert at it, and this is completely a new field. We're gonna do that. I think I'm way past 30 minutes right now, so I'll see you later. Bye bye.